Have you ever wondered how we precisely control extremely high power levels in industrial applications, or manage the flow of electricity in systems requiring robust switching? Understanding the fundamental behavior of key power electronic components is essential for designing these systems effectively. A Silicon Controlled Rectifier, or SCR, is a semiconductor device that acts as a switch, primarily operating in three distinct regions: the forward blocking region, the forward conduction region, and the reverse blocking region. Each region describes how the SCR behaves under different voltage and current conditions, dictating its utility in power control circuits. The existence and characteristics of these regions stem from the SCR's unique four-layer, PNPN, semiconductor structure. In the forward blocking region, the SCR has a positive anode to cathode voltage, but it does not conduct significant current because one of its internal junctions is reverse biased. This state is maintained until the anode voltage exceeds a certain breakover voltage, or a sufficient gate current is applied, which then triggers the device into the forward conduction region. Here, all three internal junctions become forward biased, allowing a large current to flow with a very small voltage drop across the SCR. Conversely, in the reverse blocking region, a negative voltage is applied from anode to cathode, and the device again blocks current flow, behaving like a reverse biased diode, until a reverse breakover voltage is exceeded, potentially leading to destructive avalanche breakdown. To effectively work with SCRs, you need to understand how to transition between these states. For instance, moving from forward blocking to forward conduction requires a carefully timed gate pulse, acting like the ignition key for the power flow. To return the SCR to its blocking state, after conduction, the forward current must drop below a critical holding current level, often achieved by interrupting the main circuit current or reversing its polarity. This precise control over switching between high impedance and low impedance states is what makes SCRs invaluable for applications such as phase control in AC systems, DC motor control, and power supplies. A fascinating aspect of SCRs, distinguishing them from transistors, is their latching characteristic. Once triggered into conduction, they remain in that state even if the gate signal is removed, provided the anode current stays above the holding current. This inherent memory effect simplifies control circuitry for pulsed power applications, allowing a brief trigger to initiate a sustained high power flow without continuous gate input. This behavior is a direct consequence of the regenerative feedback loop formed by the NPN and PNP transistor equivalents within its four-layer structure. Grasping these three operating regions and the transitions between them empowers you to predict and control the behavior of SCR-based circuits. This knowledge allows you to design robust power control systems, ensuring both efficient energy delivery and the protection of connected loads, ultimately enhancing your ability to innovate in power electronics.